That's the formula. You take the mass of an object, multiply it by how fast it's moving, and you get momentum. It's one of the most straightforward equations in all of physics. A bowling ball rolling down a lane has momentum because it has mass and it's moving. A freight train has enormous momentum because it's extremely heavy and traveling at high speed. A bullet has significant momentum because even though it's small, it's moving very fast. And this idea has been baked into our understanding of the physical world for over 3 centuries. So here's the problem. Light has no mass, not a tiny amount, not an amount too small to measure. 0. Exactly 0. A photon, a single particle of light, has no rest mass whatsoever. And yet light carries momentum. It pushes on things. It exerts pressure. It can move physical objects. It can change the direction of an atom. It can accelerate a spacecraft. How is that possible? If momentum requires mass, and light has no mass, then light should have no momentum. It should pass through the universe like a ghost, touching nothing, pushing nothing, unable to interact mechanically with anything it encounters. But that's not what happens. Light pushes, light shoves. Light has been pushing things around since the universe began. And the explanation for how this is possible reaches into the deepest foundations of modern physics. To understand why this is so strange, you need to understand what momentum actually is. Not just the formula, but the concept. What does it mean for something to have momentum? In the most intuitive sense, momentum is the capacity to push. It's the ability of a moving object to transfer motion to something else. If a moving billiard ball strikes a stationary billiard ball, the moving ball slows down or stops, and the stationary ball starts moving. What happened? Momentum was transferred. The moving ball gave some or all of its capacity to push to the stationary ball. The total momentum in the system didn't change. It just moved from one object to another. This is one of the deepest principles in physics. Conservation of momentum. The total momentum of a closed system never changes. It can be redistributed, transferred from one object to another, but it can never be created from nothing or destroyed into nothing. When you catch a baseball, your hand hurts because the ball's momentum is being transferred into your body. When a rocket launches, hot gas shoots out the back carrying momentum in one direction, and the rocket moves in the other direction, carrying equal momentum the opposite way. The total momentum of the rocket plus the exhaust gas stays the same. It was 0 before launch, and it's 0 after launch if you add up the momentum of everything involved. Momentum is not just a number you calculate, it's a real physical quantity. It tells you something fundamental about how objects interact and how motion gets passed around. Isaac Newton formalized all of this in 1687 when he published his Principia. Newton's laws of motion gave us the framework for understanding how objects move and interact. His second law tells you that force equals mass times acceleration. His third law tells you that for every action there is an equal and opposite reaction. And woven through all of this is the concept of momentum. In Newton's framework, momentum is always tied to mass. Always. There is no way to have momentum without having mass. If you have no mass, you have no momentum. If you have no momentum, you cannot push. This seemed like an ironclad rule. For over 2 centuries, nobody had any reason to question it. Everything in the physical world that pushed on something else had mass. Rocks, bullets, water, air, fists, hammers, planets. Everything that could exert a force through contact or collision was made of stuff. Physical material with weight and substance. The idea that something with no mass could carry momentum would have seemed absurd to Newton and to every physicist who followed him for the next 200 years. And then light entered the conversation. The first hint that light might exert some kind of pressure came not from a laboratory, but from watching comets. Johannes Kepler, the great German astronomer who figured out the laws of planetary motion, made a careful observation in the early 1600s that puzzled him. He noticed that comet tails always point away from the sun. It didn't matter where the comet was in its orbit. Whether the comet was approaching the sun or receding from it, the tail always streamed outward, away from the sun. This was strange. If the tail were simply trailing behind the comet because of its motion through space, it should point in the direction opposite to the comet's travel. But that's not what happened. The tail pointed away from the sun, regardless of which direction the comet was moving. Kepler proposed that sunlight itself was pushing the tail outward, blowing the cometary material away from the sun, the way wind blows smoke away from a fire. This was a remarkable intuition for the early 1600s. He had no theory to explain how light could push on matter. He simply observed the phenomenon and made a guess. And his guess turned out to be partly right. The dust tail of a comet is indeed pushed outward primarily by radiation pressure, the pressure exerted by sunlight. The ion tail is pushed by the solar wind, a stream of charged particles flowing out from the sun. But the dust tail, the one Kepler was looking at, is shaped largely by the momentum of light. For the next 2.5 centuries, Kepler's idea remained just that, an idea. There was no theoretical framework to explain how light could exert pressure, and no experiment sensitive enough to detect it. Light seemed weightless. It seemed like pure illumination without any physical substance. You could shine a flashlight at a wall, and the wall wouldn't move. You could stand in direct sunlight and feel heat, but no push. Whatever pressure light might exert, it was far too small for any human to sense directly. The theoretical breakthrough came in the 1860s from James Clerk Maxwell, the Scottish physicist who unified electricity and magnetism into a single theory. Maxwell's work is one of the greatest achievements in the history of science. Before Maxwell, electricity and magnetism were studied as separate phenomena. Nobody had woven all of the known observations into a single coherent framework. Maxwell did. He wrote down a set of equations, now known as Maxwell's equations, that describe how electric and magnetic fields are created, how they interact, and how they propagate through space. And when Maxwell solved his own equations, he discovered something extraordinary. The equations predicted the existence of waves made not of water or air, but of oscillating electric and magnetic fields. These electromagnetic waves would propagate through empty space at a specific speed, and when Maxwell calculated that speed from the known constants of electricity and magnetism, the number he got was approximately 300,000 kilometers per second, the speed of light. This was stunning. Maxwell realized that light itself is an electromagnetic wave. Visible light, the light you see with your eyes, is just one small slice of a vast spectrum of electromagnetic radiation that includes radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. All of these are electromagnetic waves. They differ only in wavelength and frequency, and they all travel at the same speed in a vacuum, the speed of light. But here's the part that matters for our story. When Maxwell worked through the mathematics of his electromagnetic theory, he found that electromagnetic waves carry energy. That part wasn't surprising. You can feel the energy of sunlight as warmth on your skin. But Maxwell also found something else. His equations predicted that electromagnetic waves should exert pressure on any surface they strike. When light hits a surface, it pushes on that surface, not metaphorically, physically. Maxwell could calculate the magnitude of this pressure from his equations. It was tiny, extraordinarily tiny. For ordinary sunlight striking a surface on Earth, the radiation pressure amounts to only about 4.5 micronewtons per square meter. That's roughly the weight of a single grain of sand spread over the area of a small table. No wonder nobody had felt it. No wonder nobody had measured it. The pressure of light is so small that it vanishes beneath the noise of any crude measurement. But Maxwell's equations were clear. The pressure was there. Light pushes. You might think the next step was obvious. Build a device and measure the pressure of light. And in fact, someone tried almost immediately. In the 1870s, a British physicist and chemist named William Crookes built an ingenious little apparatus that he believed demonstrated radiation pressure directly. You may have seen one of these devices in a science gift shop without knowing its history. It's a glass bulb with most of the air pumped out, containing a set of lightweight vanes mounted on a spindle so they can rotate freely. Each vane is black on one side and silvery or white on the other. When you shine a light on the device, the vanes spin. Crookes was thrilled. He believed he had proven Maxwell's prediction. Light was pushing the vanes. The black sides absorbed light and received a push. The silvery sides reflected light and received a push in the opposite direction. The imbalance caused rotation. It seemed like a perfect, elegant demonstration of radiation pressure. But it was wrong. Almost immediately, other physicists pointed out a problem. If radiation pressure were the cause, the vane should spin in the opposite direction from what Crookes observed. A reflective surface receives more momentum from light than an absorptive surface because a reflected photon reverses direction and delivers twice its momentum, while an absorbed photon delivers its momentum only once. So the silvery sides should be pushed harder, not the black sides. Crookes's vanes were spinning the wrong way. The real explanation was more mundane. Despite Crookes's efforts to evacuate the bulb, a tiny amount of residual air remained inside. When light struck the black surfaces, they absorbed more energy and heated up more than the reflective surfaces. The heated black surfaces warmed the thin gas molecules nearest to them. Those warmed molecules bounced off the black surface with greater velocity than molecules bouncing off the cooler silvery surface. This imbalance in molecular impacts created a net force that spun the vanes. It was a thermal effect, not a radiation pressure effect. The light was heating the air, and the air was pushing the vanes. The photons themselves were not doing the pushing. This misidentification caused real damage to the scientific conversation. For years, Crookes's radiometer was cited in popular accounts as proof of radiation pressure. The confusion muddied the waters and made many physicists skeptical that radiation pressure was real at all. Some wondered whether Maxwell's theoretical prediction was simply wrong. Others thought the effect might be real, but forever too small to measure, hopelessly buried beneath thermal artifacts and air currents. This is why the experiments that came next had to be so extraordinarily careful. The physicists who set out to actually measure the pressure of light knew they had to eliminate every possible thermal and mechanical effect before they could claim to have isolated the force of photons alone. And that challenge fell to a remarkably meticulous Russian physicist working at the turn of the 20th century. This prediction was deeply unsettling for physicists steeped in Newtonian mechanics. Maxwell had shown that light carries momentum, not by guessing or philosophizing, but by rigorous mathematical derivation from the fundamental equations of electromagnetism. And yet, there was no mass involved. Electromagnetic waves are disturbances in the electromagnetic field. They are patterns of oscillating electric and magnetic fields propagating through space. There is no matter in an electromagnetic wave, no particles with mass being carried along, no physical stuff being transported from one place to another. It's pure field oscillation, pure energy in transit. And yet this pure field oscillation, this thing with no mass at all, carries momentum and exerts pressure. In Newton's framework, this made no sense. Momentum equals mass times velocity. No mass means no momentum. End of story. But Maxwell's equations didn't care about Newton's formula. They predicted radiation pressure from first principles. The mathematics was airtight. If Maxwell's theory of electromagnetism was correct, and it had been spectacularly confirmed in every other prediction it made, then light had to carry momentum. Something fundamental about Newton's formula was incomplete. The experimental proof came at the turn of the 20th century. In 1901, a Russian physicist named Pyotr Lebedev performed an incredibly delicate experiment. He suspended lightweight metal vanes inside a glass vessel, from which he had pumped nearly all the air. Then he shone a focused beam of light onto the vanes and measured whether they moved. This experiment was fiendishly difficult. The apparatus had to be extraordinarily sensitive because the force of light is so small. Any residual air in the vessel would create thermal effects and convection currents that could easily overwhelm the radiation pressure, pushing the vanes far more than light ever could. Lebedev had to be meticulous in eliminating every other source of force before he could isolate the pressure of light alone. And he succeeded. Lebedev measured the pressure of light on his vanes and found that it agreed with Maxwell's theoretical prediction. Light really does push on matter. The force is tiny, but it is real and measurable. Around the same time, American physicists Ernest Nichols and Gordon Hull performed a similar experiment using a different apparatus. They used a small mirror suspended on a fine fibre inside an evacuated chamber. When light struck the mirror twisted slightly on its fibre. By measuring the twist, Nichols and Hull could calculate the force exerted by the light beam. Their results, published between 1901 and 1903, also confirmed Maxwell's prediction. The radiation pressure they measured matched the theoretical value. These experiments were landmarks in physics. They proved beyond any reasonable doubt that light exerts pressure. Light pushes. Light carries momentum. Something with no mass at all can transfer motion to something that does have mass. The billiard ball picture of momentum was broken. But how does it actually work? Maxwell's equations predicted that light exerts pressure, and the experiments confirmed it. But what is the physical mechanism? How does a wave made of oscillating electric and magnetic fields push on a piece of matter? Understanding the mechanism makes the phenomenon feel less like magic and more like an inevitable consequence of how electromagnetism works. Here's what happens. An electromagnetic wave consists of an electric field and a magnetic field oscillating perpendicular to each other and perpendicular to the direction the wave is traveling. When this wave hits a surface, the oscillating electric field does something immediate and direct. It grabs the charged particles in the surface material, the electrons primarily, and accelerates them. The electric field pushes the electrons back and forth in the direction the electric field is pointing, which is sideways relative to the wave's direction of travel. So far, this is just the electrons jiggling side to side. That alone wouldn't push the surface forward. But now the magnetic field enters the picture. The magnetic field is also oscillating, perpendicular to both the electric field and the direction of travel. And here's the key. A charged particle moving through a magnetic field experiences a force. This is the Lorentz force, one of the fundamental interactions in electromagnetism. The direction of this force is perpendicular to both the particle's velocity and the magnetic field. Since the electrons are jiggling sideways because of the electric field, and the magnetic field is pointing in yet another perpendicular direction, the resulting Lorentz force pushes the electrons in the remaining direction, which is forward, along the direction the light was traveling. So the electric field sets the electrons in motion, and the magnetic field redirects that motion into a forward push. The combination of the two fields working together creates a net force in the direction the light is propagating. This is radiation pressure. It's not one field doing the work alone. It's the coordinated action of both the electric and magnetic components of the electromagnetic wave, each playing a distinct role. The electric field provides the initial energy to move the charges. The magnetic field converts that sideways motion into forward momentum transfer. This is why the push of light is so small. The magnetic component of an electromagnetic wave is much weaker than the electric component in terms of the forces it exerts on charges. The magnetic force is proportional to the velocity of the charged particle divided by the speed of light, which for ordinary electron jiggling in a surface is an extremely small fraction. So the forward push is a tiny fraction of the sideways jiggling. But it is not zero. It is always there, always acting, always pushing matter in the direction light is traveling. Think about how profound this is. You grow up learning that to push something, you need to throw something at it. To move a ball, you hit it with another ball. To knock down a wall, you slam a heavy object into it. Every experience you have with momentum involves mass. And then someone tells you that a beam of light, something you can see through, something that weighs nothing, something that has no substance you can touch or hold, can push a physical object. It can make a mirror twist. It can deflect a metal vein. It can blow dust off a comet. And this isn't some exotic quantum phenomenon that only happens in particle accelerators. It happens every day, everywhere, all the time. Sunlight is pressing against the roof of your house right now. Sunlight is pressing against the surface of every ocean. Every lamp, every candle, every screen is exerting a tiny outward push on everything around it. You have never noticed it because the force is fantastically small compared to the forces you experience from gravity, from air pressure, from physical contact with solid objects. But it is there, always. Let me help you appreciate just how small this force is. The total radiation pressure from sunlight falling on the entire surface of the Earth is about 130 million pounds of force. That sounds enormous. Over 100 million pounds. But spread over the entire surface of the Earth, which is about 197 million square miles, it amounts to almost nothing per square meter. The gravitational force holding you to the Earth is roughly 1 trillion times stronger than the radiation pressure pushing you away from the sun. If you held a perfectly reflective mirror 1 meter square facing direct sunlight, the force of light pushing on that mirror would be roughly 9 micronewtons, 9 millionths of a newton. That's less than the weight of a single mosquito resting on your arm. Not the force of a mosquito pushing on you, the weight of a mosquito simply resting on a surface. That's how much force all of the sun's light exerts on 1 square meter of reflective surface. And yet this force is real. It can be measured. It has consequences. At the scale of tiny dust particles floating in space, radiation pressure becomes significant because the particles are so small and light that even a tiny force can change their motion. At the scale of comets, radiation pressure shapes the tail. At the scale of spacecraft with enormous reflective sails, radiation pressure can provide continuous acceleration without any fuel. And at the scale of atoms, where the mass of a single atom is extraordinarily small, a single photon can deliver a measurable kick. Radiation pressure is not negligible when you look at the right scales. So by the early 1900s, physicists faced a clear contradiction. On one hand, Newton's mechanics said momentum requires mass. No mass, no momentum. On the other hand, Maxwell's electromagnetism and careful experiments proved that light carries momentum despite having no mass. Both of these frameworks were enormously successful in their domains. Newton's mechanics predicted the motion of planets, projectiles, machines, and everything else in the macroscopic world with astonishing precision. Maxwell's electromagnetism predicted the behavior of electric and magnetic fields, the properties of light, and the existence of radio waves, all confirmed by experiment. And yet they disagreed on this fundamental point. Something had to give. Something about our understanding of momentum was incomplete. The resolution didn't come from choosing one framework over the other. It came from a revolution. A complete reimagining of the relationship between energy, mass, and motion. And that revolution had a name. It was called special relativity. And it was about to change everything. What Maxwell's radiation pressure had revealed was not a flaw in his theory. It was a flaw in the assumption that momentum must always come from mass. The Newtonian formula, momentum equals mass times velocity, was not wrong exactly. It worked perfectly well for everyday objects moving at everyday speeds. But it was incomplete. It was an approximation, a special case of a much deeper and more general relationship. And that deeper relationship would show that mass is not the source of momentum. Energy is. Mass is just one way to carry energy, and light carries energy without bothering to carry mass at all. That realization would take us from Newton's world into Einstein's world. And in Einstein's world, light's momentum is not a paradox. It is inevitable. But to understand why, we need to leave Newton's framework behind and step into a universe where space and time are not what you think they are, where mass is not what you think it is, and where the formula you learned in school is only part of a much grander equation. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would dismantle 3 centuries of assumptions about the nature of space, time, and motion. His name was Albert Einstein, and his theory of special relativity didn't just tweak Newton's physics, it replaced the foundations entirely. What Newton had built was not torn down out of spite or rivalry, it was outgrown. The universe, it turned out, played by deeper rules than Newton had access to, and those deeper rules would finally explain why something with no mass can carry momentum, why light can push, why the formula you learned in school is only a shadow of something more complete. To understand what Einstein did, you need to understand the crisis that physics was facing at the turn of the 20th century. Maxwell had shown that light is an electromagnetic wave traveling at roughly 300,000 kilometers per second. That number wasn't arbitrary. It fell directly out of Maxwell's equations, calculated from measured properties of electricity and magnetism. The speed of light wasn't just fast. It was a specific, fixed value baked into the structure of electromagnetism itself. But this created an immediate question. 300,000 kilometers per second relative to what? In Newton's world, every speed is relative to something. When you say a car is going 100 kilometers per hour, you mean relative to the ground. There is no such thing as absolute speed in Newtonian physics. Motion only has meaning when measured against a reference point. So when Maxwell's equations spit out a specific speed for light, physicists naturally asked what that speed was measured against. They assumed there must be some medium, some substance filling all of space, through which light waves travelled. They called this hypothetical medium the luminiferous ether. Light would travel at 300,000 kilometers per second through the ether, just as sound travels at about 340 meters per second through air. If the ether existed, then the speed of light should change depending on how the observer moves through the ether. If you're moving in the same direction as a light beam, the light should appear slightly slower relative to you. If you're moving against it, slightly faster. This is exactly what happens with sound. Physicists expected the same behavior from light traveling through the ether. In 1887, Albert Michelson and Edward Morley performed one of the most important experiments in the history of science. They built an incredibly sensitive device called an interferometer, designed to detect Earth's motion through the ether. Earth orbits the Sun at about 30 kilometers per second. As Earth moves through the ether, light traveling in the direction of Earth's motion should move slightly differently than light traveling perpendicular to it. The difference would be tiny, but Michelson and Morley's interferometer was sensitive enough to detect it. They ran the experiment. They got nothing, no difference at all. Light traveled at exactly the same speed in every direction, regardless of Earth's motion. They repeated the experiment at different times of day and different seasons, as Earth changed its direction of motion through space. Still nothing. The speed of light was constant, always the same, in every direction, no matter how the observer was moving. This result baffled physicists for nearly 2 decades. If there was an ether, Earth's motion through it should have been detectable, but it wasn't. Some physicists, like Hendrik Lorentz and Henri Poincaré, proposed that objects physically contract in the direction of motion, and that clocks slow down, in just the right way to hide the ether's effects. These were clever mathematical fixes. The numbers worked, but they felt artificial. They were patches on a theory rather than explanations. Einstein took a different approach. Instead of trying to save the ether, he threw it away entirely. He proposed 2 postulates. First, The laws of physics are the same for all observers moving at constant velocity relative to each other. There is no special reference frame, no absolute rest, no ether. Second, the speed of light in a vacuum is the same for all observers regardless of their motion or the motion of the light source. These two simple statements sound almost innocent, but their consequences are revolutionary. If the speed of light is always the same no matter how fast you're moving, then something else has to change to accommodate that fact. And what changes are space and time themselves. Einstein showed that if you're moving very fast relative to someone else, your measurements of distance and time will differ from theirs. Moving clocks tick slower, moving rulers get shorter. Events that appear simultaneous to one observer may not be simultaneous to another. These aren't illusions or measurement errors. They are real physical effects. Time genuinely passes at different rates for observers moving at different speeds. Space genuinely contracts in the direction of motion. This has been confirmed by countless experiments. Particles in accelerators live longer when they're moving fast. Atomic clocks on airplanes tick at slightly different rates than identical clocks on the ground. GPS satellites must account for relativistic time dilation, or their navigation calculations would drift by kilometers within hours. Now here's where momentum enters the picture. In Newton's world, momentum is simple. It's mass times velocity. But Einstein discovered that this formula doesn't work correctly when things move at speeds approaching the speed of light. At low speeds, the Newtonian formula gives results that are very close to the relativistic formula. That's why Newton's physics works so well for everyday life. Bowling balls, cars, airplanes, even rockets all move at speeds that are tiny fractions of the speed of light. At those speeds, the Newtonian approximation is excellent. But as you approach the speed of light, the Newtonian formula breaks down badly. It gives the wrong answers. And it completely fails for things that travel at the speed of light itself. Einstein derived a new relationship between energy, momentum, and mass. And this relationship is the key to everything we're talking about tonight. Most people know Einstein's famous equation, E equals mc squared. Energy equals mass times the speed of light squared. This equation tells you that mass and energy are equivalent. A small amount of mass contains an enormous amount of energy, because the speed of light squared is such a huge number. This equation is real. It's been confirmed by nuclear physics, by particle accelerators, by the sun's energy output, by everything we know about how the universe works. But here's the thing most people don't realize. E equals mc squared is the simplified version. It's the special case that applies only when an object is standing still. When an object isn't moving, it still has energy, and that energy comes from its mass. That's rest energy. The energy locked inside matter simply by virtue of having mass. But when an object is moving, the full equation is more complex. And this full equation is where the magic happens. The complete relativistic energy-momentum relation is this. E squared equals pc squared plus mc squared squared. Energy squared equals momentum times the speed of light, that quantity squared, plus mass times the speed of light squared, that quantity squared. This is the real equation. E equals mc squared is just what you get when you set the momentum to zero, when the object is at rest. The full equation has two terms on the right side. One term involves momentum, the other involves rest mass. For an object with both mass and momentum, both terms contribute to the total energy. A moving baseball has energy from its mass and energy from its motion, and these combine according to this equation. But look at what happens when the mass is zero. If you set the mass term to zero, the equation becomes E squared equals pc squared. Take the square root, and you get E equals pc. Energy equals momentum times the speed of light. Rearrange that, and momentum equals energy divided by the speed of light. P equals E divided by c. This is the answer. This is why light can carry momentum without having mass. For a massless particle, momentum doesn't come from mass at all. It comes directly from energy. If something carries energy and travels at the speed of light, it automatically carries momentum. There is no choice in the matter. The mathematics of special relativity demands it. Energy and momentum are not separate, independent quantities. They are linked. They are two aspects of the same thing, the same way space and time are two aspects of space-time. You cannot have energy in motion without having momentum, and light is energy in motion. This changes everything about how you should think about momentum. The Newtonian formula, momentum equals mass times velocity, is not the fundamental law. It's an approximation. It works beautifully for objects with mass moving at speeds far below the speed of light. And since that describes virtually everything in our daily lives, the approximation serves us well. But it is not the truth. The truth is that momentum comes from energy, not from mass. Mass is just one particularly common way for something to carry energy. When a bowling ball rolls down a lane, most of its energy comes from its mass, with a relatively small contribution from its motion. So the Newtonian formula works fine. You multiply mass by velocity, and you get a number that's very close to the correct relativistic momentum. But for light, there is no mass contribution at all. All of the energy is kinetic. All of it comes from the motion of the electromagnetic field, and all of that energy translates directly into momentum through the relation P equals E divided by C. Let me say this clearly because it matters. Photons do not secretly have mass. There is no hidden mass inside a photon that we haven't detected yet. The rest mass of a photon is exactly zero. This is not an approximation or a simplification. It is a precise statement about the nature of photons, confirmed by every experiment ever performed. If photons had even a tiny rest mass, Maxwell's equations would need to be modified. The behavior of electromagnetic fields would change in ways we would have detected long ago. The speed of light would vary with frequency. Radio waves and gamma rays would travel at different speeds. None of this happens. The rest mass of a photon is zero. You might have heard the term relativistic mass used to explain why photons have momentum. The idea is that even though a photon has no rest mass, its energy gives it an effective mass, and that effective mass is what provides the momentum. This concept was popular in the early 20th century, and it still shows up in some textbooks and popular science discussions. But most modern physicists consider relativistic mass a misleading concept. It creates the impression that photons have acquired some kind of mass because of their energy or motion. They haven't. The photon's rest mass is zero. Period. What's really happening is simpler and more elegant. Momentum doesn't require mass. The Newtonian formula that says it does is wrong at the fundamental level. In relativity, energy and momentum are directly linked. A photon has energy, therefore it has momentum. No mass is needed. No mass is involved. No mass is hiding anywhere. The photon is genuinely massless and genuinely carries momentum. Those two facts are not in conflict once you understand that the relationship between energy and momentum is deeper and more general than Newton realized. Think about it this way. For centuries, we assumed mass was the source of momentum, because every object we had ever encountered that carried momentum also happened to have mass. Rocks, cannonballs, planets, water, air, everything that pushed on other things was made of material stuff. We observed a perfect correlation between having mass and having momentum, and we assumed correlation meant causation. We assumed mass caused momentum. But it doesn't. Energy causes momentum. Mass is simply a very common container for energy, but it is not the only container. Light carries energy without any container at all. It carries energy as pure electromagnetic field oscillation, and that energy brings momentum along with it, automatically. Here's an analogy that might help. Imagine a river. A flowing river carries momentum. It can push on rocks, It can move boats, it can erode cliffs, and the momentum is carried by the water, a physical substance with mass. Now imagine a river with no water. That sounds impossible, but imagine instead a current of pure force flowing through space, pushing on everything in its path, capable of moving objects and transferring motion, but with no material substance doing the pushing. That's roughly what light is. It's a flow of energy through the electromagnetic field. The field oscillates. The oscillation propagates at the speed of light, and that propagation carries momentum, pushes on matter, transfers motion. No material substance, no mass, just energy flowing through space. This analogy is imperfect, as all analogies are. Light is not literally a river. The electromagnetic field is not literally flowing from one place to another, the way water flows downstream. But the analogy captures the essential point. Momentum does not require stuff. It requires energy in motion, and light is energy in motion. There's another way to appreciate why this has to be true. Think about conservation laws. Energy is conserved. Momentum is conserved. These are among the most sacred principles in all of physics. They have never been observed to fail. Not once, not ever. In any interaction between light and matter, both energy and momentum must be conserved. When sunlight strikes a surface and is absorbed, the energy of the light is transferred to the surface. The surface heats up. Energy is conserved. But if the light carried energy and no momentum, then momentum would not be conserved in this interaction. The surface would gain energy from the light, but no momentum. The books wouldn't balance. The universe's accounting would be off. That cannot happen. Conservation of momentum is absolute. So if the light delivers energy, it must also deliver momentum. And the amount of momentum it delivers must be exactly consistent with the relativistic equation P equals E divided by C. This is not optional. This is not a choice the universe makes. It's a mathematical necessity. If you accept that energy is conserved, that momentum is conserved, and that the speed of light is constant, then you must accept that light carries momentum. The three facts together demand it. Now let me address something subtle but important. When we say light has no mass but carries momentum, we are specifically talking about rest mass. Rest mass is the mass an object has when it is stationary, when it's not moving relative to the observer. It's an intrinsic property of the object, the same for all observers regardless of their motion. An electron has a rest mass of about 9.1 times 10 to the negative 31 kilograms. A proton has a rest mass about 1836 times larger. A photon has a rest mass of 0. Rest mass is a Lorentz invariant. All observers in all reference frames agree on its value. It is a fundamental, unchanging property. But rest mass is not the only form of energy. A moving object has kinetic energy on top of its rest mass energy. A hot object has thermal energy on top of its rest mass energy. A compressed spring has elastic potential energy on top of its rest mass energy. All of these forms of energy contribute to the total energy of a system, and in relativity, any form of energy contributes to the system's inertia, its resistance to acceleration. This is sometimes loosely described as energy having mass, and in a system-level sense, that's correct. A hot brick is very slightly heavier than a cold brick because the thermal energy adds to the total mass of the system. A compressed spring weighs slightly more than a relaxed spring because the stored energy contributes to the total mass. But this doesn't mean that individual photons have mass. A photon is not a system with internal energy sloshing around. A photon is a single quantum of the electromagnetic field. It has energy, it has momentum, it has spin, but it has no rest mass. Its energy is entirely kinetic, if you can even use that word for something that has no rest to compare against. A photon is born at the speed of light, travels at the speed of light, and is absorbed at the speed of light. It never rests. It cannot rest. It has no rest frame. There is no reference frame in which a photon is stationary. This is a deep consequence of special relativity. If you try to ride alongside a photon and match its speed, you would find that you can't. No matter how fast you go, light still passes you at 300,000 kilometers per second. You cannot catch up to light. You cannot pace it. And a photon cannot slow down to rest. It exists only at light speed. Always. This is why asking about a photon's rest mass is almost paradoxical. The photon has no rest. The concept of rest doesn't apply. But physicists have a rigorous way to define rest mass, even for particles that never rest. They use the full energy-momentum relation. If you measure a particle's total energy and its momentum, you can calculate its rest mass from the equation. For a photon, the energy and momentum are related by E equals pc. Plugging this into the full equation gives you a rest mass of exactly 0. This is consistent. This is self-contained, and it is confirmed by experiment. So here's where we stand. Newton's formula for momentum, P equals m times v, is an approximation that works for everyday objects. Einstein's full framework reveals a deeper truth. Energy and momentum are linked by the geometry of space-time. Any object or disturbance that carries energy and moves through space carries momentum. Mass is one way to carry energy, and for objects with mass, Newton's formula works well at low speeds. But mass is not the only way. Light carries energy through electromagnetic field oscillations, with no mass involved, and the relativistic equation automatically gives this energy a corresponding momentum. The amount of momentum is precisely the energy divided by the speed of light. Every beam of light you have ever seen was carrying momentum. The light from the sun carries momentum across 93 million miles of empty space and delivers it to the Earth's surface. The light from a flashlight carries momentum across the room and delivers it to the wall. The light from your phone screen is pushing against your retinas at this very moment, delivering photon momentum to the atoms in your eyes. You do not feel it, because each individual photon's momentum is unfathomably small. But it is real, it is measurable, and it follows precisely from the deepest equation connecting energy and momentum in the universe. What Einstein showed us is that the universe is both simpler and stranger than Newton imagined. Simpler because there is one unified relationship between energy and momentum that covers everything. Massive objects and massless light alike. Stranger because that relationship tells us something deeply counterintuitive. You do not need stuff to push on things. You do not need substance or weight or material. You need only energy. Pure energy traveling at the speed of light is enough to push, to shove, to transfer motion, to change the course of physical objects. Light is not a ghost passing through the world without touching it. Light is a physical agent. It interacts with matter. It exchanges momentum. It is as real, as concrete, as physically meaningful as any billiard ball that ever knocked another billiard ball across a table. It simply does its pushing in a way that Newton never anticipated. And this raises a question that takes us from the world of theory into the world of experiment. If individual photons carry momentum, can we catch them in the act? Can we watch a single photon collide with a single particle and see the momentum transfer happen? Can we prove not just that beams of light exert pressure, which Maxwell predicted and Lebedev measured, but that each individual particle of light carries a precise, definite, calculable amount of momentum? The answer is yes, and the story of how we proved it takes us into the quantum world, where light is not just a wave and not just a stream of energy, but something more specific, a particle, a photon, a discrete bundle of energy and momentum with properties as definite and measurable as those of any electron or proton. and the experiment that proved it changed physics forever. So far, we've seen this story unfold from two directions. Maxwell proved mathematically that light waves carry momentum and exert pressure. Einstein proved that energy and momentum are linked for all things, massive or massless, through the geometry of space-time. Together, these two insights explain why light can push without having mass. But there's a third piece to this story, and it might be the most remarkable one of all, because everything we've discussed so far has treated light as a wave, a continuous oscillation of electric and magnetic fields spreading through space. And from the wave picture, radiation pressure emerges naturally. But light is not only a wave. Light is also made of particles, individual, countable, discrete particles called photons. And each photon, every single one of them, carries a precise, definite, calculable quantity of momentum. Not a vague, smeared-out pressure distributed across a beam, but a specific kick delivered by a specific particle in a specific collision. And the experiment that proved this, that caught a single photon in the act of delivering momentum to a single particle, was one of the most elegant and convincing demonstrations in the history of physics. To get there, we need to understand where the concept of the photon came from, because for most of the 1800s, physicists were completely convinced that light was a wave and nothing else. Maxwell's theory described light as a wave. Experiments on interference and diffraction confirmed that light behaves as a wave. The evidence seemed overwhelming and unanimous. Light is a wave, case closed. But in 1887, Heinrich Hertz discovered something puzzling while experimenting with electromagnetic waves. He noticed that when ultraviolet light shone on a metal surface, the surface emitted sparks more easily. This was unexpected, and Hertz noted it without fully understanding what was happening. His assistant, Philip Léonard, investigated further in the years that followed and discovered something even more puzzling. When light struck certain metal surfaces, the surface emitted electrons. This was called the photoelectric effect, and its behavior was deeply strange. Here's why it was strange. If light were a continuous wave carrying energy, you would expect the energy of the emitted electrons to depend on the intensity of the light. Brighter light carries more energy, so brighter light should knock out more energetic electrons. But that's not what happened. Léonard found that increasing the brightness of the light increased the number of electrons emitted, but did not increase their individual energies. A dim blue light and an intense blue light would knock out electrons with the same energy per electron. The bright light just knocked out more of them. Even stranger, the energy of each emitted electron depended on the color of the light. Blue light produced more energetic electrons than red light. Ultraviolet produced even more energetic ones, and below a certain frequency, no electrons were emitted at all, no matter how bright the light was. You could shine an extremely intense beam of red light on certain metals, and nothing would happen. Not a single electron would come out. But the faintest trickle of ultraviolet light would immediately start knocking electrons free. This made no sense if light were a continuous wave. With a continuous wave, all that matters is total energy delivered. If you shine a dim light on a surface for a long time, the total energy delivered is the same as a bright light shining for a short time. The electrons should eventually accumulate enough energy to escape, even from dim light, if you wait long enough. But they didn't. Below a certain frequency, no amount of waiting produced any electrons at all. The energy per photon mattered, not the total energy in the beam. In 1905, the same year he published Special Relativity, Einstein proposed a radical explanation. He suggested that light is not a continuous wave. Instead, light comes in discrete packets of energy, individual bundles, quanta. Each quantum, which we now call a photon, carries a specific amount of energy determined by the light's frequency. The energy of each photon is given by a beautifully simple formula: E equals h times f. Energy equals Planck's constant times frequency. Planck's constant, denoted h, is one of the fundamental constants of nature. It was introduced by Max Planck in 1900 while solving a different problem: the spectrum of radiation emitted by hot objects. Its value is extraordinarily small, about 6.63 times 10 to the negative 34 joule-seconds. This tiny number is why quantum effects are invisible in everyday life. The energy of a single photon is incredibly small by human standards, but it is not zero, and it is definite. Each photon carries exactly one quantum of energy, and that quantum depends on frequency. High-frequency light means high-energy photons. Low-frequency light means low-energy photons. A gamma-ray photon might carry 1,000,000 times more energy than a visible light photon. A radio wave photon carries so little energy that detecting a single one is an extraordinary technical challenge. The frequency determines everything. Color is frequency, energy is frequency, and as we're about to see, momentum is frequency too. Einstein's explanation of the photoelectric effect was simple and complete. Each electron in the metal surface needs a minimum amount of energy to escape from the metal. This minimum energy is called the work function. When a photon hits the surface, it delivers all of its energy to a single electron. If the photon's energy is greater than the work function, the electron escapes. If the photon's energy is less than the work function, the electron stays put, no matter how many low-energy photons you throw at it. Each photon interacts with one electron and delivers one fixed amount of energy. A brighter light means more photons hitting the surface per second, which means more electrons escaping. But each electron receives energy from only one photon, so the energy per electron doesn't change with brightness. It only changes with frequency. Higher frequency means more energy per photon, which means more energy delivered to each electron, which means faster electrons. This explanation fit every observation perfectly. It predicted the exact relationship between light frequency and electron energy, a relationship that was later confirmed with extraordinary precision. Einstein received the Nobel Prize in Physics in 1921, not for relativity, but for this explanation of the photoelectric effect. That's how important it was. The idea that light comes in discrete energy packets, individual particles called photons, revolutionized physics and helped launch quantum mechanics. Now here's where things come together for our story about momentum. We already know from Einstein's relativity that for a massless particle, energy and momentum are related by E equals pc. And we now know from the quantum theory of light that a photon's energy is E equals h times f, where f is the frequency. Combine these two equations and you get the photon's momentum. Set h times f equal to p times c and solve for p. You get p equals h times f divided by c. That's the momentum of a single photon. It depends on the photon's frequency. Higher frequency means more momentum per photon. Lower frequency means less. There's an even more elegant way to write this. The frequency of light is related to its wavelength by the simple equation c equals f times lambda, where lambda is the wavelength. If you substitute this into the momentum equation, you get p equals h divided by lambda. Momentum equals Planck's constant divided by wavelength. Shorter wavelength means more momentum. Longer wavelength means less. A gamma ray with a wavelength of a trillionth of a meter carries vastly more momentum per photon than a radio wave with a wavelength of a meter. A blue photon with a wavelength of about 450 nanometers carries more momentum than a red photon with a wavelength of about 700 nanometers. This is remarkable. The momentum of a photon is completely determined by its wavelength, or equivalently, its frequency. Not by any mass, because there is no mass. Not by any velocity, because the velocity is always the same, always the speed of light. The only thing that varies from one photon to another is the frequency, and that single variable determines both the energy and the momentum. Every photon of a given frequency carries exactly the same energy and exactly the same momentum. It's a precise, quantized, definite amount. You can calculate it, you can predict it, and you can measure it. But predicting it theoretically and measuring it experimentally are two different things. Physicists needed a direct, unambiguous demonstration that individual photons carry definite momentum and can transfer that momentum to individual particles in a collision. And that demonstration came in 1923 from an American physicist named Arthur Compton. Compton devised an experiment of beautiful simplicity. He fired a beam of X-ray photons at a target made of graphite, a form of carbon. X-rays are electromagnetic radiation, just like visible light, but with much shorter wavelengths and much higher energies. Compton chose X-rays because their photons carry enough momentum to produce a measurable effect when they collide with electrons. Visible light photons are too gentle for a detectable recoil, but X-ray photons pack enough punch to give electrons a noticeable kick. When X-ray photons struck the graphite target, they scattered off the electrons in the carbon atoms. Compton carefully measured the wavelengths of the scattered X-rays and compared them to the wavelengths of the incoming X-rays. What he found was decisive. The scattered X-rays had longer wavelengths than the incoming X-rays. They had shifted toward lower frequencies, and the amount of the shift depended on the angle at which the X-ray scattered. This is exactly what you would expect if the photon and the electron were colliding like two billiard balls. Think about what happens when a billiard ball hits a stationary ball at an angle. The moving ball loses some of its kinetic energy to the stationary ball. It slows down. It transfers energy and momentum to the target. Now replace the billiard balls with a photon and an electron. The photon hits the electron and bounces off at an angle. In the process, it transfers some of its energy and momentum to the electron. The electron recoils, gaining kinetic energy and momentum. The photon, having lost energy, now has a lower frequency and a longer wavelength because energy is proportional to frequency. The shift in wavelength tells you exactly how much energy and momentum were transferred. Compton worked out the mathematics using conservation of energy and conservation of momentum, treating the photon as a particle with energy E equals h times f and momentum p equals h divided by lambda. His equations predicted the exact relationship between the scattering angle and the wavelength shift. And when he compared his predictions to his measurements, they matched perfectly. The agreement was precise and left no room for doubt. Photons behave as particles with definite momentum. They collide with electrons the way billiard balls collide with each other. They transfer momentum in exactly the amount predicted by quantum mechanics and special relativity. This was the final piece of the puzzle. Maxwell had shown that light waves carry momentum. Einstein had shown why massless things can have momentum. And Compton had shown that individual photons carry individual, precise, quantifiable amounts of momentum and deliver those amounts in individual particle-to-particle collisions. The case was closed. Photon momentum was not a mathematical abstraction. It was a physical reality, demonstrated in a laboratory, measured with instruments, confirmed beyond any reasonable dispute. Compton received the Nobel Prize in Physics in 1927 for this discovery. But Compton's discovery did more than just confirm that photons carry momentum. It inspired one of the most audacious ideas in the history of physics. In 1924, a French physicist named Louis de Broglie asked a deceptively simple question. If light, which everyone thought was a wave, also behaves as a particle with definite momentum, given by p equals h divided by lambda, could the reverse also be true? Could particles, things like electrons that everyone knew were solid bits of matter with definite mass, also behave as waves? De Broglie proposed that every particle with momentum also has a wavelength, and the equation was the same one, just read in the other direction. Instead of starting with the wavelength of light and deriving the photon's momentum, you start with the momentum of a particle and derive its wavelength. Lambda equals h divided by p. A particle's wavelength equals Planck's constant divided by its momentum. The same equation, the same constant, the same relationship, but applied to matter instead of light. This was a radical proposal. Electrons were particles. They had mass. They left tracks in cloud chambers. They were deflected by electric and magnetic fields. They behaved like tiny bullets in every experiment anyone had performed. The idea that they were also waves seemed absurd. And yet de Broglie's mathematics was impeccable. If the equation P equals h divided by lambda works for photons, and if nature is consistent, then it should work for everything. The relationship between momentum and wavelength should be universal. In 1927, American physicists Clinton Davison and Lester Germer provided the experimental proof. They fired a beam of electrons at a nickel crystal and observed that the electrons scattered in a pattern of bright and dark fringes, exactly the interference pattern you would expect from waves diffracting off the regular rows of atoms in the crystal. Electrons were diffracting. Electrons were interfering. Electrons were behaving as waves with wavelengths that matched de Broglie's prediction precisely. This was stunning. Matter has wavelength, not metaphorically, not approximately, precisely, quantitatively, measurably. Every moving particle, every electron, every proton, every atom, every molecule has an associated wavelength, determined by its momentum through the same equation that governs photon momentum. De Broglie received the Nobel Prize in 1929 for this insight. Think about what this means for our story. The equation connecting momentum to wavelength didn't just explain something about light. It revealed something about everything. The relationship between momentum and wavelength is not a peculiar property of photons. It is a universal law of nature. It applies to massless photons traveling at the speed of light and to massive electrons crawling through a laboratory at a fraction of a percent of light speed. The same Planck's constant appears in both cases. The same mathematical structure governs both. The momentum of a photon and the momentum of an electron are related to wavelength by exactly the same equation. This is the deepest vindication of the idea that momentum does not fundamentally require mass. If it did, the equation for photon momentum and the equation for particle wavelength would be different. They would involve different constants, different structures, different mathematics. But they don't. They are the same equation. Nature uses one relationship between momentum and wavelength for everything, massive and massless alike. Photon momentum is not an exception or an anomaly. It is one expression of a universal connection between motion and wave behavior that runs through all of physics. Let's take a moment to appreciate what photon momentum means in practical, physical terms. A single photon of visible green light with a wavelength of about 550 nanometers carries a momentum of about 1.2 times 10 to the negative 27 kilogram meters per second. That is an absurdly small number. To put it in perspective, a fruit fly buzzing through the air at about 1 meter per second carries a momentum of roughly 10 to the negative 6 kilogram meters per second. The fly's momentum is approximately 1 billion trillion times greater than the momentum of a single visible photon. A single photon is so feeble in its push that no human could ever feel it. No instrument could detect the push of a single visible photon on a macroscopic object. It's simply too small. But photons rarely come alone. A 60-watt incandescent light bulb emits roughly 100 billion photons every second. That's approximately 10 to the 20 photons per second, streaming outward in all directions. Each one carries its tiny quantum of momentum. Added together, they produce a measurable force. Not a large force by any standard. The total force from a 60-watt bulb pushing on a 1 square meter surface, placed 1 meter away, amounts to roughly 16 billionths of a newton, about the weight of a tiny grain of dust, barely visible to the naked eye. But it is measurable with sensitive instruments. And if you make the light source powerful enough, or if you concentrate the beam, or if the target is small and light enough, the force becomes significant. This is where photon momentum leaves the realm of pure physics and enters the realm of engineering. If individual photons push, and if you can produce enough of them and aim them at a target, you can move things with light. You can accelerate objects. You can slow things down. You can control the motion of matter using nothing but photons. One of the most extraordinary applications of this principle is laser cooling. In the 1980s and 90s, physicists developed techniques to use laser light to slow atoms down to extraordinarily low speeds, effectively cooling them to temperatures just a tiny fraction of a degree above absolute zero. The principle is straightforward, even if the execution is technically demanding. An atom moving toward a laser beam encounters photons coming the other direction. When the atom absorbs a photon, it receives the photon's momentum, which is directed opposite to the atom's motion. This slows the atom down slightly. The atom then re-emits a photon in a random direction. Over many absorption and emission cycles, the atom's forward motion is steadily reduced, while the random emissions average out to zero net push. The result is an atom that has been slowed from hundreds of meters per second to fractions of a centimeter per second, cooled to millionths of a degree above absolute zero. This technique earned Stephen Chu, Claude Cohen-Tanuji, and William Daniel Phillips the Nobel Prize in Physics in 1997. And it depends entirely on the momentum of individual photons. Each absorption event delivers one photon's worth of momentum to the atom. Each event slows the atom by a tiny amount. Repeated millions of times per second, the cumulative effect is dramatic. Atoms are brought nearly to a complete standstill, controlled and manipulated by nothing but light. Photon momentum, that absurdly tiny quantity we calculated a moment ago, becomes the tool that enables some of the most precise measurements in all of science. Ultra-cold atoms are used in atomic clocks, in quantum computing experiments, in tests of fundamental physics. All of it made possible by the fact that photons carry momentum. There's another application of photon momentum that takes the concept even further than laser cooling. Not just slowing particles down, but grabbing them, holding them in place, moving them around like invisible fingers manipulating objects that are far too small and delicate for any physical tool to touch. This technique is called optical tweezers, and it was pioneered by American physicist Arthur Ashkin beginning in 1986. The principle behind optical tweezers is subtle and elegant. When a tightly focused laser beam passes through a tiny transparent object, like a glass bead or a biological cell, the photons in the beam refract as they pass through. They change direction, and when a photon changes direction, its momentum changes. Conservation of momentum demands that the object receives an equal and opposite change in momentum. If the object is slightly off-center from the beam's focus, the refracted photons create a net force that pushes the object back toward the center of the beam. Move slightly left, and the photon momentum pushes you right. Drift slightly up, and the momentum pushes you down. The focused beam creates a three-dimensional trap made of nothing but light. A cage of photon momentum holding the object in place at the beam's focal point. The forces involved are measured in piconewtons, trillionths of a newton. These are forces so small that they would be meaningless for any object you can see with the naked eye. But for microscopic objects, cells, organelles, individual DNA molecules, these forces are significant. They are strong enough to hold a cell in place, to stretch a strand of DNA, to measure the force generated by a single molecular motor inside a living cell. Optical tweezers have become one of the most important tools in biophysics. Researchers use them to study how proteins fold, how molecular machines walk along filaments inside cells, how viruses attach to cell surfaces. They can pick up a single bacterium and move it to a specific location. They can hold two cells next to each other and watch how they interact. They can pull on a molecule and measure exactly how much force it takes to unfold it. All of this is photon momentum at work. Not the collective pressure of a beam on a sail, but the precise directional momentum transfer of individual photons refracting through a microscopic object. Each photon that bends as it passes through the trapped particle delivers a tiny momentum kick. Millions of photons per second, each contributing its small push, together create a stable, controllable, three-dimensional trap. Ashkin received the Nobel Prize in Physics in 2018 for the development of optical tweezers. He was 96 years old at the time, making him the oldest Nobel laureate in physics. He had spent decades refining the technique, pushing the limits of what could be manipulated with light, and the entire technology rests on a single physical fact. Photons carry momentum. Massless, weightless photons can trap a living cell in mid-fluid and hold it as gently and firmly as a pair of forceps, without ever touching it with anything material. Another application takes us from the laboratory to space. A solar sail is a spacecraft propelled entirely by the momentum of sunlight. The concept is simple. You deploy a large, thin, highly reflective sheet in space and orient it so sunlight falls on it. When a photon strikes the reflective surface, it bounces back. And here's the crucial detail. When a photon bounces off a mirror, it delivers twice its momentum to the mirror. When a photon is absorbed, it delivers its momentum once. But when it reflects, the photon reverses direction. The change in the photon's momentum is twice the original value, and by Newton's third law, the mirror receives that same twice the momentum push. So reflective sails get double the push compared to absorptive surfaces. The force is tiny. For a solar sail near Earth's orbit, the radiation pressure from sunlight provides about 9 micronewtons per square meter of reflective area. That's almost nothing. But in space, where there is no air resistance and no friction, even a tiny force acting continuously produces continuous acceleration. A solar sail doesn't need fuel. It doesn't carry propellant. It doesn't burn anything. It simply rides the momentum of sunlight, accelerating slowly but relentlessly. Over weeks and months, the velocity builds, and because the force never stops, there is no theoretical limit to the speed a solar sail can eventually reach, as long as it stays close enough to a light source to receive meaningful pressure. In 2010, the Japanese Space Agency launched a spacecraft called Ikaros, the first successful demonstration of solar sail propulsion in interplanetary space. Ikaros deployed a thin reflective sail about 14 meters across and used the pressure of sunlight to adjust its trajectory during a mission to Venus. It worked. The spacecraft measurably accelerated under the push of photons alone. No engines firing, no propellant expended, just sunlight pressing on a shiny sheet. The Planetary Society launched LightSail 2 in 2019, a small satellite that used a solar sail to raise its orbit around Earth, again propelled entirely by sunlight. These were small-scale demonstrations, proof-of-concept missions, but they proved the principle works. Photon momentum is a viable propulsion mechanism for real spacecraft. The most ambitious proposal takes this concept to its extreme. The Breakthrough Starshot initiative, announced in 2016, envisions using powerful ground-based laser arrays to push tiny spacecraft to roughly 20% of the speed of light. Instead of relying on sunlight, which is diffuse and grows weaker with distance from the sun, Starshot would concentrate an enormously powerful laser beam on a very small, very lightweight sail. The spacecraft would be essentially a chip weighing about a gram attached to a sail a few meters across. The laser array would fire for minutes, delivering a torrent of photons to the sail, each photon transferring its tiny momentum, trillions upon trillions of them accumulating into a significant push. The spacecraft would accelerate to 60,000 kilometers per second and then coast to the nearest star, Proxima Centauri, arriving in about 20 years. The engineering challenges are staggering. The laser array would need to produce about 100 gigawatts of power, roughly the output of 100 nuclear power plants. The sail must survive this illumination without melting. The tiny spacecraft must carry a camera, a communication system, and enough intelligence to navigate autonomously for 2 decades through interstellar space, where even a dust speck at 20% of light speed would release energy comparable to a bomb. These challenges may be insurmountable with current technology, but the physics is sound. Photon momentum, applied at sufficient scale, can accelerate objects to a significant fraction of the speed of light. Each of these applications, laser cooling, solar sails, interstellar propulsion, depends on the same fundamental fact. A single photon, a massless particle with zero rest mass, carries a definite, precise quantity of momentum determined entirely by its frequency. That momentum can be transferred to matter in individual particle-to-particle interactions, and when enough photons act together, the cumulative force is significant, useful, and in some cases, transformative. There is something deeply beautiful about this. The same photon momentum that Compton measured in 1923 by scattering X-rays off electrons in a laboratory is the same momentum that pushes comet tails away from the sun, the same momentum that could one day carry a spacecraft to another star. The physics doesn't change, the equation doesn't change. P equals h divided by lambda. Momentum equals Planck's constant divided by wavelength. It works for gamma rays and radio waves. It works in a tabletop experiment and across light years of interstellar void. It works for a single photon bouncing off a single electron and for trillions of photons pressing against a sail the size of a tennis court. The universality of this equation is part of what makes physics so powerful and so elegant. One relationship, derived from the intersection of quantum mechanics and special relativity, explains phenomena spanning 40 orders of magnitude in scale. And every single application, every measurement, every experiment confirms the same underlying truth. Momentum does not require mass. A massless photon carries momentum because it carries energy, and in the framework of relativity, energy in motion is momentum. The quantum theory adds precision to this, telling us exactly how much momentum each photon carries based on its frequency. The classical picture of radiation pressure, the quantum picture of individual photon collisions, and the relativistic equation linking energy to momentum all agree. They all point to the same conclusion. Light pushes, not because it secretly has mass, not because of some exotic trick or loophole, but because the universe connects energy and momentum at a level deeper than mass. Mass is a special case, energy is the general rule, and light, pure massless light, follows that general rule as faithfully as anything in the universe. But we haven't yet seen the full scope of what photon momentum means. So far, we've mostly talked about light interacting with small things, electrons, atoms, thin sails. These are the scales at which individual photon interactions become noticeable. But photon momentum doesn't just operate at small scales. It operates at the largest scales imaginable. Inside the cores of massive stars, radiation pressure from photons is what prevents gravitational collapse. In the early universe, the pressure of light shaped the distribution of matter that would eventually become galaxies. Across interstellar space, starlight sculpts nebulae and drives the evolution of cosmic structures. Light is not a passive messenger carrying images of the universe to our eyes. Light is an active participant, a physical agent that shapes the universe it illuminates. And that is where our story goes next. We've established something extraordinary over the course of this journey. Light has no mass, yet it carries momentum. It carries momentum because energy and momentum are fundamentally linked in relativity, and because each photon carries a precise quantum of energy determined by its frequency. We've seen photon momentum measured in laboratories, used to cool atoms to near absolute zero, and harnessed to propel spacecraft through the vacuum of space. But all of these examples, remarkable as they are, involve light interacting with relatively small things, electrons, atoms, thin sails drifting through the inner solar system. Now it's time to zoom out, Because photon momentum doesn't just operate in laboratories and spacecraft, it operates at the grandest scales in the universe, inside the hottest, most massive stars, across the vast clouds of gas and dust where new stars are born, in the earliest moments after the Big Bang, when the entire observable universe was a dense, seething ocean of radiation. Light is not a passive spectator in the cosmos. It is an active force, a structural agent, a builder, and a destroyer. And every bit of that power comes from the momentum of massless photons. Let's start with stars. You probably think of gravity as the force that holds a star together, and you'd be right. A star is an enormous ball of gas, mostly hydrogen and helium, held together by its own gravity. Every atom in the star is pulled toward the center by the gravitational attraction of every other atom. Left unchecked, gravity would crush the star into a tiny, dense point. But something prevents that collapse. Something pushes outward with enough force to balance the inward pull of gravity and hold the star in a stable configuration for millions or billions of years. In a star like our Sun, the outward push comes primarily from thermal pressure. The nuclear fusion reactions in the core generate tremendous heat. The gas in the core reaches temperatures of about 15 million degrees. At these temperatures, the gas particles move incredibly fast, colliding with each other and with the surrounding material, creating an outward pressure that resists gravitational collapse. The star reaches an equilibrium. Gravity pulls inward. Thermal pressure pushes outward. The two forces balance, and the star remains stable. But in the most massive stars, stars with masses 10, 20, 50, or even 100 times the mass of our Sun, something else becomes critically important: radiation pressure. In these enormous stars, the core temperatures are far higher than in our Sun. The fusion reactions are far more intense, and the amount of light generated in the core is staggering. This light, this flood of photons produced by nuclear fusion, streams outward from the core through the body of the star. And as it streams outward, it pushes on the stellar material. Each photon carries momentum. Each photon delivers a tiny kick to every atom it encounters. In a modest star like the Sun, this radiation pressure is relatively minor compared to thermal pressure. It contributes only a small fraction of the total outward push. But in a massive star, radiation pressure can become the dominant force holding the star up against gravity. Without the momentum of its own photons pushing outward, the most massive stars in the universe would collapse. This leads to one of the most important concepts in stellar physics, the Eddington luminosity limit, named after British astrophysicist Arthur Eddington, who described it in the 1920s. The Eddington limit is the maximum luminosity a star can sustain before its own radiation tears it apart. Here's how it works. As a star gets more luminous, it produces more photons. Those photons push harder on the stellar material. If the star becomes luminous enough, the outward push of radiation pressure exceeds the inward pull of gravity. At that point, the star's outer layers are literally blown away by its own light. The star cannot hold itself together. Its own photons are pushing harder than its own gravity can pull. The Eddington limit sets a fundamental ceiling on how bright a star can be for a given mass. More massive stars can be more luminous because they have stronger gravity to counteract the radiation pressure. But there's still a limit, and the most massive stars we observe in the universe sit right near this limit, balanced on a knife's edge between gravity pulling inward and light pushing outward. Stars like AY Carini, one of the most luminous stars known, radiate about 5 million times more energy than our Sun. It is so luminous that it is unstable, erupting multiple times in recorded history, blasting enormous quantities of material into space. In 1843, it underwent a massive eruption that briefly made it the second brightest star in the night sky, despite being roughly 7,500 light-years away. The material ejected in that eruption formed a spectacular expanding cloud of gas and dust called the Homunculus Nebula, which we can still see surrounding the star today. That eruption was driven largely by radiation pressure. The star's own photons pushed its outer layers into space. Stars near the Eddington limit are inherently violent. They are prone to eruptions, mass loss, and instability because the balance between gravity and radiation pressure is so precarious. A slight increase in luminosity can tip the balance, causing the star to shed its outer layers. This is one of the reasons the most massive stars live such short lives. A star like R136A1, one of the most massive stars ever discovered, with an estimated mass of roughly 200 times that of the Sun, burns through its fuel at an extraordinary rate. It is millions of times more luminous than the Sun, pouring out energy so fast that it will exhaust its hydrogen in just a few million years, compared to the Sun's roughly 10 billion year lifespan. And throughout its brief, violent existence, radiation pressure from its own photons is one of the dominant forces shaping its structure and its fate. Wolf-Rayet stars are another dramatic example. These are extremely hot, massive stars that are actively losing their outer layers to radiation-driven winds. The photons streaming out from the star's surface carry enough momentum to accelerate the outer layers to speeds of thousands of kilometers per second, launching material into space in a continuous, powerful wind. A Wolf-Rayet star can lose mass equivalent to our entire Sun in just 100,000 years, all of it blown away by the momentum of light. The star is literally evaporating itself with its own photons. Radiation pressure doesn't just shape individual stars, it sculpts the space between them. When young, hot stars ignite inside clouds of interstellar gas and dust, their intense ultraviolet light pushes on the surrounding material. The photons slam into dust grains and gas particles, transferring momentum, shoving the material outward. Over thousands of years, this relentless pressure carves enormous cavities in the cloud, hollowing out bubbles of hot, low-density gas surrounded by dense walls of swept-up material. The edges of these bubbles, where the radiation-compressed gas piles up, are often the sites of new star formation. The compressed gas becomes dense enough that gravity takes over, pulling the material together into clumps that eventually collapse under their own dense material, collapsing under gravity to form new stars. Brilliant rims where radiation is actively eroding the cloud surface. All of this architecture is driven in large part by the momentum of massless photons. Now let's go back to where this story began, 4 centuries ago. Johannes Kepler, watching comets from the early 1600s, noticed that their tails point away from the Sun. He guessed that sunlight was pushing them, and he was right. We now understand the physics completely. A comet approaching the Sun develops 2 distinct tails. The ion tail is composed of electrically charged gas stripped from the comet's surface. This tail is pushed by the solar wind, a stream of protons, electrons, and other charged particles flowing outward from the Sun at hundreds of kilometers per second, pushing the ion tail through direct particle collisions. But the dust tail is different. The dust tail is composed of tiny solid particles, grains of rock and ice released from the comet as it warms near the Sun. These particles are pushed outward by radiation pressure. Sunlight hits each dust grain, transfers photon momentum to it, and accelerates it away from the Sun. The shape of the dust tail, its curvature, its extent, its brightness, all of these depend on the balance between solar gravity pulling the dust inward and radiation pressure pushing it outward. Kepler's 400-year-old observation now has a complete and precise physical explanation rooted in the quantum mechanics of photon momentum and the relativistic equation linking energy to momentum. But radiation pressure doesn't only push things outward, away from the Sun. There is a subtler, stranger effect that actually drags small objects inward, slowly spiraling them toward the Sun over millions of years. It's called the Poynting-Robertson effect, named after British physicist John Henry Poynting and American mathematician Howard Robertson. and it is one of the most counterintuitive consequences of photon momentum. Here's how it works. Imagine a tiny grain of dust orbiting the sun. From the grain's perspective, it is moving through a field of sunlight. Because the grain has its own orbital velocity, the sunlight doesn't arrive perfectly head-on from the direction of the sun. It arrives at a very slight angle, tilted forward, the same way rain seems to slant toward you when you're driving through it, even if it's falling straight down. This aberration of light means that the radiation pressure has a tiny component pushing against the grain's direction of motion. Not pushing it away from the sun, but pushing backward along its orbit, slowing it down. And when you slow something in orbit, it spirals inward. This is the same principle that causes satellites in low Earth orbit to gradually descend when they encounter atmospheric drag. Any force that opposes an object's orbital velocity causes it to lose orbital energy and drift closer to the body it orbits. For large objects, the Poynting-Robertson effect is negligible. A boulder in orbit around the Sun is far too massive for the tiny backward component of radiation pressure to affect its motion in any meaningful way. But for particles smaller than about a centimeter, the effect becomes significant over long timescales. A dust grain a millimeter across, orbiting the Sun at Earth's distance, will spiral inward and fall into the Sun in roughly 100,000 years. Smaller grains spiral in faster. Larger grains take longer. But for any particle below a certain size, the Poynting-Robertson drag is relentless. It never stops. There is no way to avoid it. As long as the sun shines and the particle orbits, the tiny backward push of aberrated sunlight steadily drains orbital energy and draws the particle closer. This effect means that the solar system should gradually sweep itself clean of small dust particles over millions of years, and yet we still see interplanetary dust everywhere. The zodiacal light, that faint glow sometimes visible along the horizon before dawn or after sunset, is sunlight scattered by billions of tiny dust grains orbiting the sun in the plane of the solar system. These grains are continually being destroyed by the Poynting-Robertson effect, spiraling into the sun and vanishing. But they are continually replenished by comet debris, asteroid collisions, and other sources. It is a dynamic balance, an ongoing cycle of creation and destruction, driven in part by the momentum of massless photons. But let's go further back in time, much further, all the way back to the beginning. In the first few 100,000 years after the Big Bang, the universe was a very different place. It was hot, dense, and filled with a nearly uniform soup of matter and radiation. Photons were everywhere, trillions upon trillions of them in every cubic centimeter, bouncing off electrons and protons in a constant, frenzied scattering. The universe was opaque. Light couldn't travel far without being scattered, and because there were so many photons, and they were so energetic, the radiation pressure was enormous. In the earliest moments, radiation pressure actually dominated the universe. The energy density of photons exceeded the energy density of matter. Radiation was the dominant component of the cosmos, and its pressure influenced how the universe evolved. During this radiation-dominated era, photon momentum played a crucial role in determining how matter could clump together. Gravity was trying to pull matter into denser regions, the seeds that would eventually become galaxies and galaxy clusters. But radiation pressure was pushing back. Photons streaming through the dense plasma exerted pressure that resisted gravitational collapse. Matter couldn't simply fall together freely. It was caught in a tug-of-war between gravity pulling it in and radiation pressure pushing it out. This competition created sound waves in the early universe, actual acoustic oscillations, pressure waves rippling through the plasma of matter and radiation. Regions of higher density were compressed by gravity, and then the radiation pressure pushed them back outward, and then gravity pulled them in again. The plasma oscillated like a ringing bell, with photon momentum providing the restoring force. These oscillations left an imprint that we can still see today. About 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms. At that moment, photons were suddenly free. They stopped scattering off free electrons and streamed freely through space. Those photons have been traveling ever since, stretched to microwave wavelengths by the expansion of the universe. We detect them today as the cosmic microwave background, a faint glow of radiation filling all of space, coming from every direction. It is the oldest light in the universe. The cosmic microwave background is not perfectly uniform. It has tiny variations in temperature and intensity, about 1 part in 100,000, that correspond to the density fluctuations in the early universe. And the pattern of those variations, the specific sizes and spacings of the hot and cold spots, is determined by those acoustic oscillations. The oscillations that were driven by the competition between gravity and radiation pressure. By measuring the cosmic microwave background with satellites like the Planck spacecraft, we can reconstruct the physics of the early universe in extraordinary detail. We can determine how much matter there was, how much radiation, how fast the universe was expanding, and what the initial density fluctuations looked like. And woven through every one of these calculations is the momentum of photons, the radiation pressure that resisted gravitational collapse, the photon momentum that created the restoring force for acoustic oscillations, the scattering of photons off electrons that kept the universe opaque for 380,000 years. Without photon momentum, the acoustic oscillations would not have occurred. The pattern of the cosmic microwave background would be completely different. The seeds of galaxies would have formed differently. The entire large-scale structure of the universe, the arrangement of galaxy clusters and voids and filaments spanning billions of light years, bears the fingerprint of photon momentum in the early universe. Think about how astonishing this is. The same momentum that Compton measured in a tabletop experiment in 1923, the same momentum that pushes a 1-gram solar sail through the inner solar system, shaped the structure of the entire observable universe. The same equation, P equals h divided by lambda, applies to a single X-ray photon scattering off a single electron, and to the collective pressure of all the photons in the primordial plasma, pushing against the matter that would become every galaxy you can see through a telescope. The physics does not change. The scale changes. The numbers change. But the underlying truth is the same. Photons carry momentum. That momentum is real, and its effects span the entire history and structure of the cosmos. Let's bring this journey to its conclusion by thinking carefully about what all of this means. What does it mean that light carries momentum? What does it tell us about the nature of light and about the nature of reality? It tells us that light is not nothing. This might sound obvious, but it's worth stating explicitly because our everyday intuition strongly suggests otherwise. Light seems insubstantial. You can't hold it, you can't weigh it, you can see through it. It doesn't seem to resist your motion or press against your skin. Compared to the solid, tangible objects that fill our lives, light seems like the absence of darkness rather than the presence of something real. But light is real. It is as real as any material object. It carries energy. It carries momentum. It carries angular momentum, meaning it can make things spin. This is not a metaphor or an analogy. Individual photons carry a measurable quantity of angular momentum, the rotational equivalent of the linear momentum we've been discussing all along. Linear momentum is the capacity to push something in a straight line. Angular momentum is the capacity to make something rotate, and photons have both. The angular momentum of a photon is connected to its polarization. Light can be polarized in different ways. Linearly polarized light has its electric field oscillating back and forth in a single plane. But circularly polarized light is different. In circularly polarized light, the electric field vector rotates as the wave travels forward, tracing out a helix like a corkscrew threading through space. Each photon of circularly polarized light carries one unit of intrinsic angular momentum, called spin. This spin is always the same magnitude, regardless of the photon's frequency or energy. Whether the photon is a low-energy radio wave or a high-energy gamma ray, it carries the same amount of spin angular momentum. The direction of the spin determines the handedness of the polarization. Right circularly polarized photons spin one way. Left circularly polarized photons spin the other. When circularly polarized light strikes an object and is absorbed, the photon transfers not just its linear momentum, but also its angular momentum, making the object rotate. In 1936, American physicist Richard Bethe demonstrated this by shining circularly polarized light through a thin quartz plate suspended from a fine fiber. The plate twisted. Bethe measured the torque and confirmed it matched the theoretical prediction exactly. Today, physicists use beams of light engineered with specific angular momentum profiles to rotate microscopic objects in the laboratory. Tightly focused beams carrying orbital angular momentum can spin tiny particles like miniature turbines, controlled entirely by light. These optical spanners, cousins of the optical tweezers we discussed earlier, can rotate individual cells, drive micromachines, and probe the mechanical properties of biological structures at scales no physical tool could reach. So light doesn't just push things forward, it can spin them too. Every photon carries both linear momentum, the ability to shove, and angular momentum, the ability to twist. Both are real, both are measurable, both are consequences of the electromagnetic field, carrying genuine mechanical properties despite having no mass at all. It exerts pressure, it transfers motion, it interacts with matter in every way that matters for physics. The electromagnetic field, the entity that light is a disturbance in, is one of the fundamental structures of the universe. It is not an abstraction, it is not a mathematical convenience, it is a physical thing that fills all of space and whose excitations, photons, carry energy and momentum from one place to another at the speed of light. It tells us that the universe does not require mass for momentum. This is perhaps the deepest lesson. For centuries, we assumed mass was the essential ingredient for physical interaction. To push, you need stuff. To carry momentum, you need weight. To exert force, you need matter. Light shows us that this assumption is wrong. Energy is the fundamental currency. Mass is one denomination of that currency, a particularly common and familiar one. But energy comes in other forms. Electromagnetic field energy, gravitational potential energy, kinetic energy, and any form of energy in motion carries momentum. The universe is more flexible, more creative, more surprising than Newton's framework allowed. It doesn't restrict momentum to lumps of matter plodding through space. It allows momentum to be carried by waves of pure field oscillation, by disturbances that propagate through the void at the fastest speed the universe permits. It tells us that the old boundaries between matter and energy, between stuff and light, between substance and radiation, are not as sharp as we once believed. In the modern physics born from Maxwell, Einstein, Planck, and Compton, matter and light are not fundamentally different categories. They are different expressions of the same underlying quantum fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Both carry energy, both carry momentum, both interact with other fields. They differ in important ways. The electron has rest mass, and the photon does not. The electron can sit still, and the photon cannot. But these are differences within a unified framework, not differences between separate realities. Matter and light are cousins. They play by the same rules. They obey the same conservation laws. They exchange energy and momentum with each other in every interaction, from the absorption of a photon by an atom to the annihilation of an electron and a positron into pure light. And it tells us something about every photon that has ever reached your eyes. When you look at the sun, or at a lamp, or at a star in the night sky, The photons entering your eyes have traveled some distance to reach you. From the lamp across the room, the journey is trivial, a few meters traversed in a few billionths of a second. From the sun, the journey is about 8 minutes and 20 seconds across 93 million miles of empty space. From a distant star, the journey might have taken years, decades, centuries, or millennia. And every one of those photons, from the moment it was created to the moment it was absorbed by the molecules in your retina, was carrying momentum. It was carrying a tiny but real capacity to push, to transfer motion, to interact with matter. When that photon is finally absorbed by a molecule in your eye, it delivers its energy and its momentum to that molecule. The molecule changes state. A chemical signal cascades through your nervous system. An electrical impulse travels to your brain. You see? That act of seeing, that seemingly passive experience of simply looking at something, is a physical interaction. It is a momentum transfer. Every photon that enters your eye pushes, however gently, on the atoms it strikes. You are being pushed by every beam of light that falls on you, pushed by the sun, pushed by your desk lamp, pushed by the glow of your phone screen, pushed by starlight that has been traveling for centuries. The forces are absurdly small. You will never feel them, but they are there, always. There is a tendency in popular science to describe photons as ghostly or ethereal, as though they exist in some halfway state between real and unreal. But photons are not ghostly. They are as real as bullets, just much smaller and much faster. They carry energy. They carry momentum. They exert measurable forces. They can heat objects, move objects, destroy objects. Concentrated laser light can cut through steel. Focused sunlight can ignite fires. Gamma-ray photons from nuclear reactions carry enough energy to damage DNA and kill living cells. Light is powerful. Light is physical. Light is real. And here is perhaps the most beautiful part of the story. The reason light can do all of this, the reason massless photons can push mirrors and shape nebulae, and hold up stars and sculpt the structure of the universe, is not because of some exotic trick or exception to the rules of physics. It is because of the rules of physics, the deepest rules, the ones that connect energy to momentum, that link space to time, that unify matter and radiation under a single mathematical framework. In that framework, momentum doesn't require mass. Energy is enough. And light is energy, pure energy, propagating through the electromagnetic field at the fastest speed the universe allows, carrying with it the capacity to push on anything it touches. The next time you step outside on a bright day and feel the warmth of sunlight on your face, remember what you've learned. That warmth is energy, and that energy carries momentum. The sun is not just warming you, it is pushing you, gently, imperceptibly, but physically, measurably, really pushing you. Photons that were born in the heart of a nuclear furnace 93 million miles away have travelled for 8 minutes through the vacuum of space, each one carrying its tiny quantum of momentum, and they are pressing against your skin at this very moment. You are being touched by light, pushed by something that has no mass at all, and the reason that's possible is one of the most profound truths physics has ever revealed. In this universe, you do not need substance to push. You do not need weight to carry force. You need only energy. And light is energy in its purest, most elemental form. Light is not weightless nothingness drifting through the void. Light is one of the most fundamental things in the universe, a real carrier of energy and momentum, shaping matter from the scale of single atoms to the scale of the entire cosmos. And every photon that reaches you from every star in the night sky is proof. Thank you for joining me on this journey into the heart of light and momentum. If you found this exploration valuable, a like or subscribe would mean a great deal. It helps me keep making these deep explorations of physics and the universe. And remember, The next time you look at a beam of sunlight streaming through a window, you're not just seeing light, you're seeing momentum. Real, physical, massless momentum, crossing space at 300,000 kilometers per second, carrying with it the power to push on everything it touches. Good night, and may you never look at light the same way again.